Hi everyone. I wanted to take a moment of your time to consider more closely the origins of atmospheric pressure and how to think about the relationships between pressure and height that we developed in class. Specifically, we had been considering how the pressure depends on height, and we expected as we moved up in height away from the Earth's surface, the pressure should decrease. We justified this prediction with reference to our actual experiences, but we also hypothesized that atmospheric pressure comes from the mass of atmospheric gases pressing down under Earth's gravity. And so as we move farther away from the Earth's surface, there is less atmosphere above us, and so there will be less atmospheric pressure. Using this as a starting point, we derived an equation for the dependence of pressure, which we called P, on height, which we called Z. We are not going to go through this derivation again, as you already saw it in class, but I think it is worth exploring the ramifications of this equation. The first thing to do is to try to envision what this equation looks like with respect to the behavior of pressure as a function of height. And the best way to do this is to plot it. This plot then requires two axes, one where we account for the height. Since this is our independent variable, let's put it on the x-axis, as is typically done. The other quantity of interest is the pressure, which will be our dependent variable, and we will place it on the y-axis, again following convention. Then all that remains is to plot the dependence of pressure on height as expressed by our equation. The shape we're looking at is called an exponential decay. The exponential refers to the fact that the independent variable, in this case z, is an exponent, and the decay comes from the fact that there is a negative sign in front of the independent variable. This means that as the independent variable gets larger, the dependent variable, in this case pressure, will get smaller. If you're having trouble seeing this, we can rewrite the equation, remembering that a negative sign in an exponent means that we are dividing by that quantity, which yields this form, and very clearly shows that our height away from the surface, as it increases, the pressure will decrease. We can unpack this equation a bit more by considering the constants that are used, in this case P0 and H0. Sometimes we call these P0 and H0 as well. P0 is the pressure when our height is at 0, or when z equals 0, and we are at the surface of the Earth. On our y-axis, we have set this as 1 atmosphere. Of course, the accuracy of this depends on several other variables, such as temperature, but for now let's assume that we have chosen all of these variables so that the pressure at the surface of the Earth really is 1 atmosphere. This is why the curve we have drawn crosses the y-axis at 1 atmosphere, because at this point, z is 0. You are probably somewhat comfortable with the fact that P0 is where we cross the y-axis. But how about the other constant, H0? What is this? Well, in class, we called this the scale height and set it equal to the gas constant times temperature divided by gravitational acceleration on Earth times the average molecular mass of our atmosphere. We also noted that these quantities end up giving a value of 8,800 meters. Great! What does this even mean, really? One thing to note is that we are multiplying our independent variable by the inverse of this number. In other words, we are effectively scaling z by this number. This is why we call it the scale height. Also, when we have an exponential decay, the thing that we are multiplying the independent variable by, we often refer to as the decay constant. The idea is that the value of this number controls how fast the function goes to its minimum value, in this case 0. In other words, how sharp is the curvature? It also means that many other interesting properties of the function are related to the value of the decay constant or the scale height. For instance, imagine we were at the scale height of 8,800 meters. What would this mean for the pressure? Well, we can draw a line from z equals 8,800 meters to our function, and where it intersects the function, that is our pressure. That, of course, is how line plots work. But we can also calculate this value, and since z equals h0, the exponential must be equal to 1, which also means that the value of p at h0 is p0 divided by e, or just over 1/3 the value of the pressure at the Earth's surface. This is a nice relationship to remember for this type of exponential decay? When the height equals the decay constant, we are 1 over the e of the initial pressure value. If you go into science and engineering, this is a relationship that will crop up over and over again. And having a basic idea of how the curve behaves will help you get an intuitive sense for the physical behavior that is being described. Of course, this is not the only value of interest. Oftentimes, we are also interested in understanding where our dependent variable reaches 1/2 its starting value, because this also helps us get a sense for how the function is behaving with respect to the physical things of interest. And again, we can note that we can simply draw a line from the y-axis until we cross the function, as shown here, and then we can extend it down to get a value of z. But again, we can do some math to help us find the value of z. In this case, we note that we know the value of the function, which is 1/2 p0, and so we can rearrange to find z, which will end up being the natural log of 2 multiplied by the scale height. So again, we see that the decay constant crops up. Thus, the reasoning for thinking about the decay constant, or what we are calling the scale height here, is that it gives us a good sense for how the curve is behaving. We can frame this in terms of some real-world examples. Maybe we can consider what's happening at the summit of Mount Everest. The top of Mount Everest is 8,850 meters, which is very close to our scale height. If we are familiar with how exponential decay functions work, then this is a very convenient number, because if we note the similarity between the height of Everest and our scale height, and we are comfortable with the fact that the exponential function will reach 1/3 its value when we reach the decay constant, then we instantly know that the pressure of the atmosphere at the top of Mount Everest is roughly 1/3 the pressure at the surface of the Earth. This also explains why people use oxygen masks when climbing Everest, because if the pressure is 1/3 that at the surface of Earth, then the concentration of oxygen is also 1/3 that at the surface of Earth. Perhaps it would be interesting to look at the elevation of State College and to think about the concentration of oxygen there that we live with compared to those that live at sea level, or maybe in Denver, the Mile High City. And just to bring this all home, we should remember that the reason the pressure is less is that the air above Mount Everest is less. We can envision this column of air that stretches above it using the dots shown here, where the concentration of air will increase as we move closer to the Earth's surface. Remember, pressure is increasing, and so the concentration will increase, as the ideal gas equation tells us it should. The reason that there is less pressure at Everest and a lower concentration of gases is simply that there is a shorter column of air. This agrees exactly with the intuition that started us down this journey and produced our decay curve. So it's satisfying to see it crop up again. But there is one last thing I'd like to ask. What happens if we go below the surface of the Earth? I grew up in California, which is home to Death Valley, the lowest point of land on Earth, minus 86 meters below sea level. What should happen here? Our picture of an air column gives us an intuitive answer. There will be more air above us, and so we should expect more atmospheric pressure in Death Valley. But what do we do with the negative value for z? Is this a problem for our pressure equation? Maybe you can look at it and decide what happens if we plug in a negative number for z. What will happen to the pressure? Can we handle that? How will it compare to our P0? And don't worry, we will also give you some practice thinking about this on the homework. So until next time, I hope you enjoy a new perspective on the atmosphere that surrounds us and appreciation for the power of plotting functions and thinking about their shapes.